Welcome back. Now coming to the another Indian example from Himalayas, and this satellite photo is from 20 kilometers from Chandigarh, and here what we found was quite interesting along this river valley, and this river is named as Jajra river, and here if you see this way, this is a rail track which goes to Shimla. Now let us see over here what happened, okay, and what we were able to mark this. Now this is the area where we were looking at for the signatures of the active faults, but we found something else, okay, here. It was quite interesting. Now this photograph was taken in 1978. Now of course I was interested in mapping the active fault here, but I found something very interesting here. Please note down, try to remember that what I am showing in this photograph, which was taken in 1978. There is a rail track here, that is the rail track which I was talking about. This takes you to Shimla, and then this portion here is the fault scarp here, and you see the river valley here, this stream which is coming up. This is a Jajra river, and you are having the beautiful lesser Himalayas which are sitting at the back. We have terraces. These are the terrace. These are all terraces. Okay. These are all terraces. Now, as if you remember carefully, we were talking about that we in the beginning of the lectures. Okay, I showed some example of what happened in Uttarkashi floods. Okay, that people like to construct their houses on the flat surfaces and then close to the river and all that, and those are your river terraces. Now this photograph was clicked in 2000, okay, and you can match little bit, but not exactly, because I was unable to take the photograph from the exact location, but you can see the rail track here. There is the same rail track. Some trees have grown here, and few of the trees have come here on this area, and then this peak here is this one, the same peak. But if you can see the terraces here, there are a lot of houses you can see on the here, a lot of construction. Another photograph I will show, you can see from here, okay, same hilltop, same hilltop here, same hilltop here. But you see in the river beds, you are having a lot of construction which came up, and this is hardly 20 to 30 years. Okay. So this is what we call the improper construction, okay, without having understanding that what will happen if you have the cloudbursts in this region, or you are having the flooding in this region. Okay, this all houses which are sitting on the terraces, okay, and the town planners, they allowed them to construct these houses very close to the river beds. Okay, will face problem, severe problem during the major floods. Okay, though they have not experienced until now, but the floods or the events which we have, unusual events we have experienced in recent past, okay, like Uttarkashi, we can have the similar one here also. Okay, if you see one photograph here, what you can, this is again, you can see the valley, whole valley has been filled up with the construction. Okay, now this is the part which I was a bit worried about, that if you are having the erosion from the base here, okay, this house which is sitting on the top here at the corner will come up, okay, will, like, these boulders will come out, and then this, and definitely the house will collapse. Okay, and that what similar thing happened in the Uttarkashi flood. So this is an improper practice of construction. Coming to another type of landslide or the mass movement is your fall. Okay, and these are mainly related to the coarser material which we call the rock falls. Okay, so these are again the movement is very sudden, because it will just the fractured rocks will fall down from the cliff. Okay. So, mainly it occurs where you are having most of the weak plains and you are having the jointed hard rocks. Okay. And in high altitude regions where you have problems with the freezing and thawing effect, you may face this type of landslip very frequently. An example of the rock block from US, okay, which rolled down and mashed up the whole house. Okay. But this is an example from India, okay, close to Nainital, with a huge rock block which came down and which destroyed the house. Okay. So, we have to be extremely careful where we are locating our houses or the settlements. Okay. Then toppling is another phenomena which is associated with the mass moment, and this will happen where you are having mostly the jointed rocks. Okay. And that will facilitate the toppling of the material, and the movement will be from like end over end motion. Okay. So, end over end motion will be something like this. Okay. So, this will topple down, and so if you are having the fractured material, you may face this type of landslide or the mass movement, even though the rocks are massive in nature. Okay. So, occurs along the steep slopes with vertically jointed. Okay. And the another one which we looked at was if you are having the bedding planes which are dipping towards the slope. Okay. Okay. So, these are the vertical joints and those are the bedding planes which are we are talking about. So, landslide in steep hard rock terrain mainly depends on the orientation of and nature of the discontinuities. Now, discontinuities are mainly the joints, bedding planes, etc. Okay. Now, in general, the geological structure that influence the mass faulting are the planes of weakness in rocks. Okay. Planes of weakness may be bedding planes in sedimentary rocks or foliation planes in metamorphic rocks. So, this or if these rocks are jointed, okay, then you may have the problems of the landslides. Okay. Now, flow, it will be sudden, okay, but flow further can be categorized into two depending on the speed. Okay. One is slow, okay, one is rapid. So, rock creep is very slow movement, okay. Soil creep is again a slow movement, okay. And the earth flow solifluction is relatively faster, mud flows are faster and towards rapid, debris flows are extremely fast and debris avalanches. Okay. So, fall category can have depend on the speed, okay, how fast they are going to slip. Okay. We will see a couple of examples. Solifluction mainly will be seen in the higher altitude areas. Solifluction is a downward movement of wet soil along the slope under the influence of gravity, and most commonly in glacial terrains during summer. So, this will happen because what happens, the uppermost part will melt, whereas the lower part remains frozen, okay, and that will result into the increase in pore water pressure again due to melting and gradual slip of the ground which is melted, okay, on the top of the, and this mostly it moves like in the form of lobes. Okay. So, this here the example which you can see, the uppermost portion of the soil which melted and the subsurface remain frozen, the uppermost will slide down along the slopes, okay, and it will move very much in the form of the lobes, okay, but the movement is very slow. So, this is an example of the solifluction. Then another example is a soil creep. Okay. This is an extremely slow downward movement and it will take time to be seen or observed on surface, but in some locations we can easily make out if we are having to get we are getting some cracks which are coming up, or there are tilting of the lamp post or the trees also, that are the indicators of the creep going on in that areas. Okay. And this is extremely important for the civil engineers to notice. Okay. So, this is an example of the soil creep over here, and this again is showing that bending of the tree trunks. Okay. So, this can help us in identifying that this area is slowly creeping. Okay. An example of the rock creep, very slow creeping is taking place. Now, mud flows, we have talked about this. So, I will just move ahead. So, this occurs when slope material becomes so saturated that the cohesion bond between the particle is lost. Okay. So, this is an example again. We have talked about the mud flows, the lahar flows. They are very rapid type downslope movements that involves mud flows from volcanic ash. Okay. So, mud flows can occur on surface with very gentle slope, okay, because the internal particle friction resistance and the cohesion is negligible on that slope. Okay. So, this may occur on even and very gently sloping surface. Okay. So, occurs where the fine textured sediments and soil mix with water to create a liquid flow. Okay. So, if you are having excess amount of water coming up because of the percolation or because of some other reasons, then you may experience the mud flow in that region. Okay. Then coming to the subsidence, it represents the downward movement of the surface. Okay. It may occur due to plastic outflow, as we have seen the example of the Good Friday earthquake of 1964 Alaska. Subsidence due to plastic outflow, this is the same example of the Good Friday earthquake, or you are having subsidence due to collapse. It occurs due to extensive pull out of large volume of underground water. Okay. So, you are extracting groundwater at a very high rate, okay. That can also result into the subsidence, or due to the subsurface solution activity in the limestone terrains. Okay. So, one is large removal of groundwater, another is the solution activity because of the in the limestone terrain. Okay. This is typical topography which one can see in the limestone terrain, which we call the karst topography, and you have this subdued one. Okay. These are all, you may have potholes here, which is due to the subsurface solution activity. Subsidence, and this is what happens when you keep on extracting the water, extensive water. So, if you look at the profile of the soil and the groundwater, what you will see is that you have a vadose zone and you have a zone of saturation, okay, where you will have the pores, and pores are occupied with the water. Okay. And this is what the area, you can say, the aquifer from where you will pump up the water. Okay. Now, if you keep on pumping the water and the recharge is very low here, eventually what will happen, that this vadose zone will have no water left out. Okay. And this will result into the compaction, because this is the space which is available between each grains, which are still are occupied by the water. But if you have removed this, this will result into the, that is the water saturated sediments will be compacted. Okay. So, this will happen because of the excess removal of groundwater, and this can result into the collapse of the area. The next example, this is of the karst topography. Okay. And you can see the huge, these are the small potholes, okay, small potholes in the limestone terrain, but this one is the huge one, okay. And you can make out the size of this pothole. This is from US, based on the size of this truck here, okay, the car here. It's a huge pothole which came up, okay, because of the the subsurface solution activity. And this is one of the famous example because of the excess extraction of groundwater. Okay. This is Leaning Tower of Pisa in Italy, and this was because of the groundwater withdrawal. Okay. So, we need water for the growing cities, but we may experience or we may result into the associated hazard because of this. Now, control and stabilization. So, very simple methods have been adopted over the past and still we are doing. The most important is that the slope factor. Okay. So, you reduce the slope, okay, flattening of slope, surface drainage control, try to remove water as fast as possible from the surface, subsurface drainage also you can apply. Okay. Earth buttress and counterweight fills to block the slip of the material on the surface, construction of retaining walls, light weighted fills. You should not fill up back the area that what we are doing the counterweight fills, okay, within the heavier material. Okay. Then removal of the unstable material. If you understand that this area is having the material which is unstable, try to remove it and fix it up using the counterweight fills. Okay. Then earth stabilization and reinforcement. You can do vegetation cover, okay, wire mesh confined. This confinement can be used when you are having major rock falls in the areas. You can use that, and in combination of both. Okay, you can have the wire mesh, and then you can also put the you can do the reinforcement of the areas. Okay. So, flattening of slope, this is one of the most commonly seen method. If you go into the hilly terrain, you will find small terraces along the hill slope. Okay. So, if suppose you are having the slope like this, you will find that you have the small farms like this, okay, constructed. Now, this is basically a very old practice. So, you will have the agriculture here going here, but what eventually they have done is they have reduced the slope. Okay. They have reduced the slope. So, this you will find very common in the hilly terrain, okay, that the agricultural practices the people have used to do this for cultivation, and they have eventually reduced the slope. Okay. So, most common method dealing with the landslides is to flatten or recreate the slope to a stable angle. Okay. By unloading the top material of the slope and reduce some of the driving forces, which essentially are gravitational. Okay. In some areas where right of way is limited, okay, or that is the encroachment upon housing development, these methods have been altered. Okay. So, what people have done is they have created the bench slopes. Okay. So, for example, in some residential areas it was difficult to do that sort of slope reduction. So, over the time what they did is that they constructed the benches here, okay, or what we call the berms, okay, and finally they came up with this. Okay. So, you have beautified the area and you have retained the slope also. Okay. So, this is what one of the best method can be done, okay, in the residential areas. There is again a photograph which we are showing on the way to Nainital. So, massive landslides you will come across in the areas. Okay. So, this is what they have done. Okay. They have constructed the retaining walls and they have tried to reduce the slope here, because this is the massive landslide which has been seen on the way. Okay. There is a close up of that. Now, surface drainage, you can try to construct the drainage on the surface and try to remove or the water as fast as possible, because you are not allowing the water to percolate down into the ground, okay, or on the slope, okay, and that will reduce the area from having chances of landslides. Okay. There is an example from Japan where you can see the I may be having better photograph or not, maybe this one. Okay. So, you have the drain which is coming up out down here, okay, and then they have cut the slope in different benches. So, they have reduced the slope here and they have tried to stabilize, and in some places they have also put the fences here, okay, or the wire mesh to, if something happens and if some block roll downs, it will be blocked here. Okay. So, again this is the example of the drainage which is coming up, and they have reinforced, they have put concrete on the surface to protect that, and at various locations where they have cut and reduced the slope, they have put such wire meshes. Now, subsurface is again, people have been doing that. Suppose you are having the porous material sitting here, okay, and this material will have like is having the capability of absorbing or occupying more water when it is coming or percolating down, this may slip. Okay. So, as soon as what people have done, that they have put artificial horizontal drain pipes, okay, which can remove the water, percolating water, which is and does not allow it to collect in this layer. Okay. So, that can also reduce the chances of slope failure, because water reduces the shear strength and increases the lateral forces and increase the weight of the mass on the slope. Okay. So, during heavy rain you may face these problems, okay, and such areas may have the chances of the landslide. Okay. So, these pipes are perforated pipes which will keep on accumulating the water which is getting percolated down here and will be poured out directly along the slope. Okay. Then another example of retaining walls you can do, you can cover the slope with cement and reduce the infiltration and also strengthen the slope. So, various methods are employed to stabilize or strengthen the internal shear strength of the soil and to achieve the reinforcement. This includes cement grouting, chemical injection or lime stability, etc. So, using different materials, people have used different methods. Wire meshes are confined where you are having the chances of rock falls. Okay. So, commonly used on rockfall areas to protect the boulders moving down onto the surface or along the roads and all that. Okay. Other part is that people have also tried to put the wire mesh into the area of loose material. Okay. So, one is you are putting the wire mesh here to protect the boulders rolling down, and another is you are putting the wire mesh and covering it with the cement, so that you strengthen this slope which is occupied by the loose material. This is an example again from Japan, where they have constructed the drains. Okay. Vegetation cover is another way of protecting the slope. So, planting exert both hydrological and mechanical control on the slope stability. Okay. Vegetation cover reduces or disperse the subsoil moisture, and the root tends to act as an anchor. Okay. This is important. Okay. The subsurface of anchor to the subsurface material together to prevent the slope failure. Planting types varies from grass to bushes and trees, but as I told that you should not put a very heavy vegetation on the slope, which will increase the overburden. So, vegetation covers are incorporated in most slide prevention plans as the complementary solutions. Okay. So, along with what you are doing, the benching part and all that, you can add the vegetation as a complementary solution. Okay. Planting should include different type of covers which varies root depth to avoid skin type sliding. Okay. That may occur at the base of the roots. Okay. So, this is again the botanical people can help in choosing the plant type and all that. Okay. So, constant watch of landslides is again an important part. Okay. So, this is in March 1987. This again in March on 19th, this was on 4th, this one on 19th, and this one is on 17th April, okay, on the same year it slipped, okay, and finally you have the major one which is coming on March 1990. You can see the more slip has developed here, okay. So one can also have the constant watch on this, okay. And nowadays with the advancement of science, people are using GPS, okay, to watch such type of slips, okay, or taking multiple aerial photographs to see that whether the area is slipping or not and how much it is creeping or slipping over the time. And finally, this was the thing which happened in 93. This whole area slipped out, okay. But this was a very small one, but this is one of the good example to understand that how we can constantly watch and monitor the landslides and landslips. So identification and conservation of landslide prone areas, okay. Now landslides can be detected and mapped through a combination of field research and the study of high resolution satellite data as well as aerial photographs, okay. A geologist use professional judgments and knowledge of local geology and topography to classify area into landslide hazard categories, okay. Maps highlighting hazard zones can be prepared from high resolution satellite data by preparing digital terrain models, okay, or digital terrain maps. This can help, and as I told that one can also use the GPS to monitor the landslip, okay. Steeply inclined slopes should be identified and categorized depending on the degree and amount of slope angles, okay. So here the most important part which we can talk about is the one is the local geology, okay, the topography, that is the slope, okay, fine, and then based on that you can categorize your areas in the hazard zone. So there is a map which shows prepared based on the digital elevation model, okay, which indicates the high slope areas, and these are the different colors which shows the heights of the region, okay. So this is the DM which has been prepared, and based on this one can also classify that's which areas are having which type of material and which type of slide can be dominated there, okay. Whether some of these slides are dormant, some of them are active, okay, and then further you can have classification based on the elevation, okay. So this type of classification can be done using satellite data, but nevertheless one should go to field and try to understand that what is the geology in that part. Slope stability classification, if you take class 1, this may vary from place to place again, but in general you can say that slope with active landslides, okay, is class 1, where material is continuously moving and scars are fresh and well defined, okay. Movement may be continuous or seasonal. Then class 2, slopes are frequently subjected to new or renewed landslides. Movement is not a regular seasonal phenomena. A recurrence interval is up to 5 years or so, but this can happen only if you are having constant watch on that area. Third category, you can say class 3, slopes are infrequently subjected to new or renewed landslides. A recurrence interval is greater than 5 years, okay. And class 4, slopes with evidence of landslide or the historical landslide or the past landslide we can see, but has not undergone any movement in past 100 years, okay. Class 5, slope which shows no evidence of any previous landslide activities, but are considered likely to develop in future, and this will happen because if you have a slope and you have geology which could favor the landslide in future, okay. And then class 6, you have slopes which shows no evidence of previous activity, are considered to be more stable, okay. So I end here. Thank you so much. We'll continue in the next class. Okay.